3.3, separation of variables. The first thing I'm going to do is I'm going to write down the 11 steps. I added up all the steps that you typically take to solve Laplace's equation through this brute force method of separation of variables. And I came up with 11 steps. So it is a fairly complicated recipe, but hopefully reviewing this video after you've seen me solve a couple of these, you'll have an appreciation for how they all kind of fit together. So the first step is you write the equation. So that would be something like you have Laplace's equation. This is in this is in Cartesian coordinates, of course. The second step is you try to eliminate some of the terms by symmetry. What do I mean by that? Well, if your problem has like there's no dependence on z in the boundary conditions that you're going to have, then it simply can't vary by z. It has to be the same for any z, and so you can just cross off that term, and now you're only solving a differential equation with two variables. So it becomes much easier the more you can get rid of. The next thing you do is you write down those boundary conditions. And you write them down because you're going to have to refer to them again and again. So you want to make sure you get it right. After we have the boundary conditions, we can write V as a sum over I of some terms that have to do with X and some terms that have to do with Y. And if you still have Z, there's some terms that have to do with Z, right? And this is generally what the solutions end up looking like. So, and for the next couple steps, we're just going to consider if we just had one of these terms, how they'd behave in this equation. So step 5 is we plug it in and then divide by. And how does that look like? Well, the second derivative with respect to x of x, y, and z, since x is the only term that varies with x, the y and z terms come out. So you have y, z, then you have to leave the x in there, and then you divide by x, y, z. So these terms cancel, and then by the same logic you get d squared by dy squared in terms of y divided by y, and you get d squared by dz squared of z divided by z, and that equals 0. And at this point you have basically three separate terms, and each of these terms depend only on one variable. This one depends only on x, that one depends only on y, and that one depends only on z. And it shouldn't take much effort to understand why these all have to be constant. So just imagine you hold x and z constant and vary y. Well, these two values are not going to change, but and so this value can't change if we're going to maintain a value of 0. And you can do that for any of the other terms. So all of these must be some constant that add up to 0. So now we have to pick, and the constants are going to basically be something like k squared or minus k squared, something squared, because you're taking the second derivative, so you're going to be applying something twice, of course. And of course you want to have it so they can't all be positive. One of them at least must be negative, or else it's not going to work. Or at least one of them must be positive, or at least one of them must be negative. Now you have simple differential equations. D by dx of x, this is squared, is equal to, let's say you chose a positive term, right? And you're going to get the same thing for x and y and z. These are fairly simple to solve in Cartesian coordinates. In spherical coordinates, not so much, but it's definitely not difficult. Step 8, and I'm going to run out of room, aren't I? Now you apply the boundary conditions to eliminate or set the constants. As you might guess, that for a differential equation where you have a d squared by dx squared, you're going to have two constants. And so in Cartesian coordinates, you're going to have 6 constants altogether. Hopefully you can get rid of some of those to simplify your equation so it's reasonable. Finally, you combine everything back together, and some of the constants will be multiplied with each other. In that case, you just use a single constant for the multiplication of the two. And then hopefully at that point you have some complete solution, right? So if you have a problem where you have one of the boundary conditions is actually a function, then if you have a complete set of solutions for that boundary condition, then you can, if you have a Fourier series, basically when you set that boundary condition to 0, then you have a complete solution. So you can say I can solve for basically any value of that boundary condition. And finally, you take advantage of the orthogonal nature, if any, of the functions, so you can pick out the constants. Okay, it's a rather broad overview, and this really won't make sense to you right now, but this is kind of sort of a roadmap. You'll watch as I go through these problems. I'm going to follow these steps bit by bit. Some of them kind of behave a little funky depending on the problem, but hopefully you get a good grasp of what's going on here. Thanks for your time.